Hello. So on this video, I'm going to show you how to determine the axial force, or N, and then the shear force, might be known as D or V, and the bending moment, or M, diagrams. Okay, so first things first that I'm going to do is I'm going to draw the reactions at A and B. So since at A we have a hinge, I'm going to assume that VA goes upwards, and there's a horizontal reaction HA. Okay, and at B, since it's a roller, it has a vertical reaction perpendicular to the inclined plane. So I have VB cosine of alpha and VB sinus of alpha. The next step, what I'm going to do is calculate HA, VA, VB. I forgot to mention that this is a uniformly distributed load of 5 tons per meter. And I also want to mention about the sign convention. So I have positive whenever your force goes upwards and goes to the right direction. So using my equilibrium equations, which is sigma F to the vertical direction equals to 0, positive VA, and then a positive VB cosinus of alpha, and then minus 2 tons, and then minus 5 times 2, since it's a uniformly distributed load, equal to 0. The next equation will be sigma F to the horizontal direction equals to 0. Positive HA and a minus VB sinus alpha equal to 0. And the last, I need to find that sigma moment at a certain point equals to 0. So I'm taking like sigma and B equals to 0. Better make sure that VA goes either clockwise or counterclockwise to V. And since VA will go clockwise, and it's going to be positive VA times 5 meters. I'm going to see here like my concentrated load of 2. It's going to be counterclockwise, so it's going to be minus 2 times the distance, which is 1 plus 1 plus 2 plus 2. I still have like this uniformly distributed load in here of 5. It's going to have like this concentrated load in the middle of 5 times 2, which is 10 tons, which gives us like 1 meter and 1 meter. Okay, so I'll have minus like 5 times 2, which makes 10 here, times the distance, which is 1 plus 2 equals to 0. 8.4. And then I'll get like my VB equals to 6 tons, which makes us able to find that HA equals to 4.8 tons. So the next step is we're actually going to draw the diagrams. So we're going to first make our axial force. So we have like this at C, which doesn't have axial force, and then at A it have like HA, which goes to the right, since we have like a positive HA right here. So at A I will have axial force of 4.8 tons. I have like here, which is a minus VB sinus alpha, which will be also 4.8 tons. Okay, so now on the shear force, or the D diagram. First we have like at C negative 2 tons, so I'm going to plot my 2 tons right here, and then it's going to be 2 tons until it reaches A. Well, at VA we have like a positive 8.4 tons, so it's going to be 6.4 tons right there. You know, it's going to be a straight line until it reaches D. Well, at D until E, it's going to be a uniformly distributed load. So at E, it's going to have 6.4 minus 5 times 2, which is 10. So I have like a minus 3.6 right there, all the way to the end here. So we've managed to draw the axial force and the shear force diagram, and the last step is to draw the bending moment diagram. Since at C, the 2 tons times 0 meters, then the moment at C should have been 0, and the moment at B should have been 0. At A, minus 2 tons. How can I say it's minus? Because here's the illustration. If you have like a beam, and then you give it like a load like here, and it's going to bend like downwards, and whenever your beam is going to go downwards, then the bending moment should have been negative bending moment. But if you put like a positive flow like right here, your beam is like it's going to smile, then you have like a positive bending moment. Okay, so at C we have like a minus 2 because it's going to make our beam like go downwards like this. So we have minus 2 times the distance to A, which is going to be 1 meter. So I'll have a minus 2 times 1 equals to minus 2 ton meters. And then at D, what we have is a negative 2, since it goes downwards, times 2 meters, like the distance to D. And then we have like positive VA times 1 meters, which is also the distance from VA to D, equals to 4.4 ton meters, which we get from minus 2 times 2 plus 8.4, which is 4.4 ton meters. And forget this, which is negative. So at E, since we have minus 2 times 4 meters, we have positive VA times 3 meters, and we have this uniformly distributed load. So I have minus 2 times 4 plus VA times 3, and I have minus 5 times 2 times 1. So maybe right here, 7.2 ton meters. But since it's in UDL, so we are going to have a parabolic bending moment. So it maybe goes around like the moment at B, because it's not a pinned end, so it's going to be 0. And the way you actually check that is that you multiply, you know, minus 2 times the distance to B plus VA times the distance to B, and minus 10 or minus 5 times 2 times the distance to B, which is 3 meters. Okay, if you actually notice that there's a mistake on drawing this, this is because whenever your D is 0, like here on this point right here and on this point right here, there's going to be a maximum moment. And the way you actually calculate that, you need to find out the distance here. I'm going to call this like X. So we're going to calculate X. So if the distance from here to here is 2 meters, then I'll have this part right here, it's going to be 2 minus X, which means I have a triangle of like this. So 6.4 over X equals to 3.6 over 2 minus X. And what you're going to do with this distance is that you're going to find the moment at this position. So we're going to, you know, calculate moment of X, where X is 1.28. So I have a minus 2 times the distance, which is 1 plus 1 plus this X right here, which is 1.28, 3.28. And then I have like a positive VA times the distance, which is 1 plus X, And then I have this uniformly distributed. It's not going to be like 10 tons anymore because we only see like 1.28 meters from there. So a minus of 5 times 1.28 and then times the distance. The distance of the UDL, it's going to be like half of the total length. So it's going to be 1.28 over 2. It's going to be our maximum positive bending moment. Okay,